Okay, so we've talked about covariant derivatives, so I'll make a small point about this, and then we'll go into the Lie derivative discussion that I promised this morning. So what I want to talk about here is the covariant derivative along the curve, because that's an operation that occurs a lot, and I think we need to talk about it so that we recognize that later. So the idea that we introduced before was that, well, we can take we can take a vector field and differentiate it in pretty much any direction. So if we have a coordinate system, we can differentiate it along t, along x, along y, along z, and that implies that we can take differences in all possible directions. But sometimes we have a direction that's actually specified in some discussion, and that would be defined through a curve. So we already have the partial derivative of the covariant derivative of a vector given in terms of partial derivative and in terms of a connection. So we've already talked about that, and as I said, that sort of implies that we have a vector field defined in an open region that allows us to take derivatives in all directions. But sometimes we have a situation where we are interested in taking a derivative along a direction specified by a curve. So here we would have a curve gamma. I'm calling it gamma, and it's going to be a parameterized curve. And that curve will have a tangent vector. I'll call it t, t the vector. And what we would like to do is to take a derivative in that very specific direction. So the curve gamma is going to be described as a parameterized curve, as I said. So there's going to be an assignment for each value of lambda, the parameter. Parameter lambda goes up along the curve, and for each value of lambda, lambda equals 1, lambda equals 2, lambda equals 5, we have a specific point on the curve. So that's what this notation describes. And the tangent vector is simply going to be the derivative of those functions with respect to lambda. And of course, t is tangent everywhere on the curve. So when we're talking about the covariant derivative along the curve lambda, we're really talking about taking those covariant derivatives, but projecting them in the direction of the tangent vector. So the notation that I like to use for this is the big D here that tells you that we're talking about a covariant derivative as opposed to an ordinary derivative. And I would define that to be the projection along t the vector, of the covariant derivative of the vector instead of any other direction. We project the covariant derivative in that very specific direction. And that's, the covariant derivative along the curve. So that's something that arises a lot, for example, when we talk about the velocity vector of a curve, or when we talk about the acceleration vector of a curve, we would be talking about derivatives defined purely along the curve. So we would define it like that. And so we can re-express this in various ways. So we can, use the fact that the t vector, the tangent vector, can be defined in terms of those function derivatives. So we can rewrite it like this if we wished. And, well, it basically means exactly the same thing. But we can re-express it in yet more ways. So we can keep the t vector alone here, but make this more explicit using the decomposition in terms of partial derivative and connection. So we can write it like that. And that we can rewrite it in a slightly different way. So here we're talking about the partial derivative of the velocity, I'm calling it velocity, but of the vector field, the partial derivative of the vector field projected in the tangent direction. And, if we were working in ordinary vector calculus, that would be recognized as the ordinary derivative of the vector field with respect to the parameter lambda. So that projection that we do here at the level of the partial derivative is basically the same thing we did up here, but that defines the total derivative of the components v beta in the direction of lambda. So finally, a way of expressing all of this would be to write it in this form over here, where the big D derivative would be an ordinary derivative plus a gamma term, a connection term that makes the operation covariant as opposed to illegitimate from a tensorial point of view. So those are all notations that can be encountered, and we'll do quite a bit of that in the near future in the next few minutes. All right. Yes, thank you very much. So as my students in Guelph know, I do this on purpose to make sure that you're awake. So congratulations. All right, so yeah, so different ways of writing the same thing, but basically the important concept here is that we're talking about a vector that's differentiated along a curve as opposed to in, arbitrary directions. And one more point that I'll make before moving on is just to say that there's some, it's a bit of a pedantic point of notation, but when I write it like this, I'm sort of understanding this as saying that here's a vector field that I could have differentiated in all directions, but I choose to project it along, I used to project the derivative, I actually project the derivative along one specific direction given by the curve. So when I write it like this, it's sort of understood that the vector field is defined in a big region so that I can differentiate it in all directions, not just along the curve, but in other directions as well. But then I choose to project in one specific direction. This notation doesn't necessarily mean all of this, because if I write, if I just relate this to what it stands for at the end of the calculation, what I'm required to do here is to differentiate the vector field only with respect to lambda, which means that I only care about the derivatives along the curve. So I hope you get my meaning here. So here, when I write it like this, I need the vector field to be defined on the curve only. And only derivatives along the curve are then defined. If I write it like this, I'm sort of understanding that the vector field is defined away from the curve so that I can differentiate in all possible directions, and then and only then take a projection. So there's a slight, different emphasis of meaning when you write it like this or like that. It's minor, but I think it's good to think about that sometimes, when sometimes you're given a vector field just on the curve and you would have no idea of how to differentiate in directions across from the curve or away from the curve. You would only be able to differentiate it along the curve. So just a small point of notation, but I think we all know what we're doing here, so it's not that big of a deal. Yep.
Thank you. Somehow what you mentioned clarified my problem, but something is bothering me, and it's so when we just have the covariant derivative, is that we are comparing the vectors at two different points. So we are moving in some direction. Mm-hmm. And that object is a covariant object. And then when we are talking about directional, if I'm calling it correctly, derivative, mm-hmm. It means that it matters in which direction I want to move. But this, I thought that the derivative itself should be somehow invariant. I mean, it shouldn't matter if I move, I don't know, in two different passes from 2 points on my manifold, for example. If I go like this or like this, then I want to compare those tensors or both vectors and then define the derivative. I thought they should be the same, but now with the directional derivative, I feel that they wouldn't be the same if I.
Well, so the idea of the directional derivative is that instead of allowing ourselves to differentiate along all possible directions, we pick a direction as given to us by the curve. So it's understood that here, as we're going to compare the vector at different points, we're going to be moving along a very specific sequence of points. Now, You could always think of comparing a vector here to a vector here by considering a different sequence of points between the two. And it's certainly true that, well, for infinitesimal displacements, that wouldn't make a difference. But still, the directional derivative along that curve versus the directional derivative along that curve would be very different because you're evaluating the vector field along very different paths. So there's no, I don't think it's a surprise that that would give you different, different things.
Infinitesimal distance, then they would be the same.
Oh yeah. So I mean, yeah. So you're asking how we're supposed to take the limit between two neighboring points, and I think it's true that the answer shouldn't depend on how you take the limit, but here we're supposed to take the limit, along the curve given, as opposed to a limit that would be, I don't know, proceeding along a different path. So it's just more, more specified in this case. Yep, good question. Thank you. Okay, so that's the last thing I wanted to say about the covariant derivative. And of course, we're going to be using this a lot. Now I want to talk about Lie derivative. So I've talked a little bit about this morning. I promised this to be, that there would be a discussion on this. So let's go into it. And that's a very, very, useful and, very powerful way of talking about derivatives of vectors and tensors that, perhaps surprisingly, does not involve a connection. So it's an operation that can be defined in a perfectly well-defined tensorial way with all operations that are perfectly legal and everything, but doesn't require a connection. So it's more primitive because we don't need this extra structure. We can do it, without that. And it's a very beautiful construction, and it's not just, nice and pretty from a geometrical point of view. It's actually extremely useful for physics. And even in the undergraduate curriculum, I think that, there would be fields of physics that would benefit from having introduced the Lie derivative as one of the central, conceptual aspects. But, I'm not gonna bore you with that little, rant. Okay, so what's the Lie derivative? Well, first of all, it's a derivative operation without a connection, which means that we don't have to introduce this extra structure whether or not it's going to be related to the metric. So it's actually more primitive than the covariant derivative because it's defined purely in terms of what we would find on a manifold if, it didn't have a metric, if it didn't have a connection. If all it had was vectors, we would be able to define this. The only thing that we need, though, are two vector fields. So in order to define that thing, we're going to need two vector fields. And I'm going to call one Xi, and the other one I'm going to call A. And Xi is going to be my favorite one, and A is going to be the thing I want to differentiate with respect to the other one. So here's the idea. So I'm going to define things. I'm going to set this up purely geometrically. And then when we're ready, we're going to do a little calculation that shows us what this is all about. So I have two vector fields, and therefore I have two sets of integral curves. So let me draw the first set. So I'm going to select C as my sort of first vector. And I will say that, well, I have a vector field at every point in some open region of space. So I have one vector over here, another vector over here. So that's all pre-specified for us. We have the vector field. And with the vector field, I have a whole set of integral curves to which the vector field is everywhere tangent. So I didn't draw this very well. Let me do that again. I'll draw the curves first. It's going to be easier. So here's a few integral curves, but you have to imagine that we have a whole continuum of them. So through each point, there passes one curve. And the vector field Xi is going to be everywhere tangent to those curves. So that's the first step of the construction. So I'm drawing here the integral curves of Xi. And those I'm going to describe as a parameterized curve like this, where t is going to be the parameter. So t is going to be a parameter that's going to be running up the curve. And for each value of t along each curve, I have a specific assignment of coordinates. And if I have that, then of course I have that c alpha is going to be the derivative of those functions here with respect to t. All right, so that's the first thing that we get. We get a vector field and its whole set of integral curves through each point. So we're going to be using that. And what I'm going to do here is to pick a point. I'm going to pick a point P. That's where I'll be defining my Lie derivative. And at that point, while I have the second vector field, so let me draw it here. I have the second vector field defined at that point. It's defined everywhere, but it's defined there in particular. And through that point, there's going to be the integral curve of that vector field. So let me draw that. I'm going to draw the integral curve of that vector A that, looks like this. And then I could draw the vector field everywhere else. I could draw integral curves everywhere else, but I'll just stick to that one vector over here and the integral curve that passes through P. So this is the integral curve of the vector A through P. And that I'll describe also in a parameterized form. So there's going to be functions of a second parameter S. And my vector A through that point is going to be the derivative of those functions with respect to the new parameter. So that's the second step. And now I'm going to add a little bit of fine print so that I can set up the calculation later a little bit better. I'm going to just do a little bit of a refinement on this so that we can set up the calculation later in the most transparent way. So let's see. So let's say that through P here, the parameter of that integral curve of C was equal to 1. And then later on, I would have t equals 2. And then prior to that, I would have smaller values of t. So I'm setting up a parameterization here for this integral curve. And I also have a parameterization for all the other ones. But I'm going to use the freedom to change t by a constant on each curve so that I can arrange for the value of t right here to also be equal to 1. That's where the integral curve of A intersects that integral curve of C. And I'm making sure that this will happen at a constant value of the t parameter. All I have to do to arrange this is to see whatever parameterization I had there to begin with. And all I have to do is to slide t by a constant in order to change whatever value used to be here to the desired value of 1. So that's what I'm going to do here. And I'm going to do the same thing over here. So I'm basically adjusting the parameterization so that this integral curve crosses those ones with a constant value of their parameter. Can always do that, and there's no harm in doing it, and it's going to simplify our life in a few moments. And then I have the parameter S that runs along that integral curve. Okay, so that's part of the setup. We're going to do the next step. And the next step, what I'm going to do, and bear in mind that what I'm trying to do here is to find a way to compare two vectors that initially are at different points by bringing one of them to the same point. So that's the whole point of the exercise, to come up with a derivative operation that is legitimate, but without introducing a connection. And my second point is going to be up here somewhere. So that's going to be my second point. And what I want to do here is to find a way to compare a vector that used to be here to a vector that's here. So that's where I'm going with all of this, so that you can sort of follow the thread of that whole setup here. Okay. So what am I going to do? So what I have here is one integral curve of the vector field A, the one that passes through P. And what I'm going to do is to take that curve and I'm going to slide it up along those curves, the integral curves of c, by a constant t offset. So let me draw this. So we have the original curves that are tangent to c, to which c is tangent, I should say. We have the one integral curve of a that we just drew, passing through p. We have arranged for the t parameter to be constant along that curve. And what I'm going to do is to just take that point over here, and I'm going to slide it up. That used to be t equals 1. I'm going to slide it up to t equals 2. Except that, I'm thinking of doing this in a continuous way. So I could pick whatever value I want for delta t, and I would get a brand new curve out of this. So I take that point over here, slide it up by 1. Take that point over here, slide it up by 1. Take that curve over here, slide it up by 1. And that will define for us a new curve. I'm going to call it the dragged curve. And what you have to imagine here is that here I'm doing it for a delta t equal to 1. But I could do it for any value of delta t, and we have to think that, eventually that delta t will be very small. That's how we're going to be taking the limit to a derivative. So that is going from a curve at t equals 1 to a curve at t equals delta t, 1 plus delta t. So that initial curve over here was tangent to the vector field A. That was, an integral curve. That was the definition of the first curve. That dragged curve over here is not going to be tangent to the vector field that would be defined up here. A is defined everywhere, and it's going to be defined at that point Q in particular. But the vector field at Q is not going to be tangent to that dragged curve. There would be no reason for that to happen unless, the vector field A would have very specific properties. So what I'm saying here is that at Q, our vector field would have a direction like this, and it's not going to be a tangent to that drag curve, because the drag curve that we're doing here, the dragging that we do, has nothing to do with keeping it lined up with the vector field A. But that drag curve will have some tangent vector that I'm going to call a dragged version of the original A down here. And the drag version of A, which is required to be tangent to the drag curve, is going to be, in general, different from the original vector field A evaluated at Q. And that's the key. We have two vectors defined at Q. We can take a difference and use that to define a derivative. And all of that has been made with elementary operations that are completely legal from a geometrical point of view and does not involve a derivative, does not involve a connection. So is the construction pretty clear? Yep.
You're not mentioning, talking about coordinates at all.
No, the coordinates are sort of underlying there, but they're not playing an essential role yet. Yeah, so geometrically, it's really take a curve, tangent to A, drag it forward, define a new tangent vector there, and compare it to the original vector field at Q, and use that difference to define a derivative. And I might as well write it down. The Lie derivative, I'm going to denote Lie derivative of A along C. That's the notation. That's some kind of curly L. C is the direction in which we take the derivative, because we're moving up along those integral curves. We're differentiating the vector field A. By definition, this is the limit where delta t goes to 0 of the difference between, let me make sure I have the order right. The difference between the original vector field, A at Q minus the dragged version of A at Q. So we're taking a difference at the same point, therefore it's a legal vectorial operation. And we're taking the difference of those two vectors, taking the limit where delta t goes to 0, to define the Lie derivative at the point P. So of course, in the limit, Q goes down to P, so by taking this difference, we're actually defining the derivative at P. So that's the definition, and it's perfectly geometrical, it's perfectly legal, it's perfectly fine, and the construction is such that we never have to introduce a connection into it. So that's how we can define a derivative, geometrical derivative of a vector field without a connection. And you'd think that there should be some merit to this, there should be some ways of applying this in ways that are very important because it's so primitive and I would say very geometrical. The ideas that we're using here are very geometrical, so it's very much in the spirit of differential geometry. So any questions at this point? Yeah?
So what is it? Up to this point, I thought that we need to set up coordinate, and that drag is basically coordinate transformation, but now I'm seeing that it's more general.
It's a lot better than this. So in the book, I present it as something having to do with the coordinate transformation, and it's really bad. I mean, it's really not a very good way of describing it, and I'll have to apologize for that in a second edition of the book that may come out someday. I will certainly change this, but yeah, it's very important to understand that this is a very geometrical construction that has nothing to do with the coordinates, but we are doing something with the parameterization when we're doing this, because that's how we're doing the dragging of the curve.
And now it seems too good to be true. I mean, what is the price for this stuff? I thought before it's the coordinate, but now even if you don't need that, then...
Well, it's not too good to be true, but the catch is that we can only do this when we have two vector fields. So for the covariant derivative, we needed one vector field and a connection, so that's how we could derive the, define the derivative. Here, in order to do that, we need two vector fields. We can't really, we can't do it with one, we have to do it with two. Yeah. Yep?
Connection is a connection on form. Can we think of the covariant derivative as a Lie derivative with respect to this vector field that is this connection on form? If we also had a metric, maybe we can recast it in a vector field. No? Doesn't work that way?
Sorry, I didn't get your answer.
It's not, right? This is a connection on form also, right? It's gamma, on this basis vectors, tetrads. Right? Can you think of it as a Lie derivative along this vector field that is you can get from this gammas if you lower the indices with the metric, for example? No?
Not to my knowledge. But maybe there's more to be said about this. I don't know. Okay. Yeah. Well, that's what I was explaining here, right? So here I've dragged the curve. I've defined the drag vector field here to be tangent to the drag curve. And I'm saying that this vector over here defined at Q is going to be in general different from the original vector field defined at Q. So we have a vector field A that's defined everywhere, in particular at P and Q. So at P it looks like this, at Q it looks like this. And that original vector field at Q is going to be different from the dragged A vector that we get as being tangent to the drag curve.
But isn't A defined as dz over ds, so it has to be tangent like s?
So that defines the integral curves. Right. So we have the vector field everywhere. We have also with it the integral curves. So that drag curve is not an integral curve of the original vector field through Q. So that integral curve would be tangent to A. That drag curve is the one that I get from the original integral curve at P that I've dragged forward by a delta t.
Right, A has to be tangent to something, right?
Yeah, so there would be tangent curves. There would be integral curves of A. I'm just not drawing it. I've drawn one. I'm not drawing the second one. It doesn't play a role in this discussion. Right. Okay, so we're all good so far? Okay. Well, a lot of the work has been done, so we're going to see what that translates into. Before I do that, I will just put a little bit more fine print. So we've talked about the S parameterization on the original integral curve. I have to set up a parameterization on the drag curve. And what I'm going to do here is to just say that, well, if I'm going to draw it separately. So this was the original set of integral curves to C. This was the original integral curve to A through P. This is the drag curve. So this is the dragged curve. This is the integral curve to A. Through P. And what I'm saying here is that, well, suppose that the value of S here was equal to 1, the value of S here was equal to 2, the value of S here was equal to 3. I'm going to say that I'm going to set up a parameterization on that drag curve so that S is going to be the same value here, here, and here. So the parameterization on that curve was given to us by doing the integrating this differential equation over here. So that's how we get the integral curves from the vector field. So the parameterization here is already given. But when I drag the curve, I'm free to specify whatever parameterization we want on that curve. And I'm just saying that that parameterization up here is going to be such that S is going to be preserved along each of those integral curves. So that's just a little bit of fine print, and I'm going to be using this in just a moment when I actually set up the calculation that goes with this. But at this point, I think what's really important is the geometrical picture that arises from that. Okay, and then I'm going to delay that for a little bit, but I'm going to show that this Lie derivative amounts to the derivative of the vector field A along C, expressed in partial derivatives, minus the derivative of C along A. So that definition here, we're going to show in a moment, implies that result, which says that I differentiate A along the direction of the Xi vector, and then I differentiate Xi with respect, in the direction of the A vector. And the difference between the two is what I mean by the Lie derivative of what comes out of this definition. And here there's a couple of surprising things. Partial derivative, partial derivatives. So that's not a proper tensor. This is not a proper tensor, but the difference is a proper tensor. And one way to actually prove this is to, I made a point that I could do all of this without introducing a connection, but we could put it in since we have it. And what I'm saying is that I can re-express all of this in terms of covariant derivatives and get exactly the same result. The only difference is that now we would make each term properly a tensor, this one and that one. We didn't have it here and here, but here we have it. And the promise to you, and I'll ask you to check that, is that if you expand this out and bring out the connection terms, you're going to find that they cancel out because of that minus sign. So in this expression over here, the gammas cancel out. So we could define the Lie derivative in terms of covariant derivatives, but that's a little bit like missing the point because we can do it without. And even though individually these objects are not proper tensors, or proper vectors, I should say, the difference is because the Lie derivative has been defined properly geometrically and is guaranteed to deliver a nice vector. So the only thing that remains to be proved is that, well, is the definition really giving us that? And that's a calculation that we'll do in a few moments.
What do you mean by proper tensor?
I mean something that is a tensor in the sense that we've defined it in the morning lecture as a linear functional of vectors and covectors, all of that stuff that we've talked about this morning.
Does a regular derivative also linear?
Uh, yeah, so a derivative operation is linear, but it's not a properly tensorial operation. So another way to state this is that a tensor is something that must transform in a very specific way under coordinate transformations. I hate to say those words, but that would be one way of settling the issue. And everything involving a partial derivative, as we talked about this morning, doesn't satisfy this requirement. So that's a proper vector, that's a proper vector, this is not, but the difference is. And that comes from the fact that it really satisfies this definition, which is defined in terms of proper geometrical operations. We're not taking we're not subtracting vectors that are defined at different points in a manifold. Okay, so that's one thing. The other thing that you may notice here is that if I factorize a minus sign, I'm getting exactly the same operation, but inverted. So this is exactly the same thing as the Lie derivative on C in the direction of A. So, the operation of Lie derivative on vectors is antisymmetric this way. In mathematical notation, this is represented as a bracket. You have a bracket between two vectors, and that's the explicit notation for that. Okay. So in a moment, we're going to want to derive this based on the definition. We're going to want to show that, it really gives us that. So I'll do that in a few minutes. But before I do that, I want to see how we can extend this from vectors to other objects like covectors and scalars and tensors. So we're going to extend the definition of the Lie derivative to other objects, again, using Leibniz as our, as our guide to do this. All right. So bottom line is that we're given we've provided a very geometrical definition for the Lie derivative in terms of those operations that we defined here. And we'll show in a moment that the definition gives us this involving non-vector, but the difference of two non-vectors, that turns out to be a vector. We can rewrite it in an equivalent way in terms of covariant derivatives if we want to. In this line, we're guaranteed that the gammas will cancel out, and you can, prove that for yourself. And then we have this antisymmetry property that I think is obvious from this result over here, not so much from the definition itself. So we're good at this stage? Yep.
Isn't there a division by deltas?
Oh, yes, thank you. I forgot the delta t over here. Thank you. Okay, so we'll come back to this, but now I want to extend the definition to other things. So on scalars, well, there's no big mystery here, so we don't have to be careful when we compare the values of scalars at different points because we can take them without having to worry about transporting them in any way. So the Lie derivative of a scalar quantity, by definition, that's just going to be the derivative along the integral curves. So I can write it like that, and that's a perfectly fine scalar. So that's the definition of the Lie derivative on a scalar. So it basically means the directional derivative of the scalar along the curve that's tangent to xi, or the curve to which xi is tangent. So no big mystery here. But then we would like to extend it to other objects. So for example, a covector. So if we're in the business of extending the concept of Lie derivative to covectors, then we're going to make use of the Leibniz property. And the idea is just follow exactly the same sort of calculation that we did previously. We're going to implement it in exactly the same way. So I'm interested in working out the Lie derivative of a covector omega. So what I'm going to do is to combine omega with v, a vector v to form a scalar, and then I know what this operation is. And then I'm going to break it up into a product of Lie derivatives using the Leibniz property. And then from all that, we'll be able to conclude something about the Lie derivative acting on omega. So let's work this out. So this is a scalar, so I can rewrite this as the directional derivative of that product. And this I can make explicit. So first we have the derivative of omega, and v gets multiplied, and then we have omega that comes along, and we have the directional derivative of v. So that's the first, the first line we can write down. And that's just saying that, well, the Lie derivative acting on a scalar is just the ordinary derivative, and that certainly obeys the Leibniz rule. And then we're actually going to implement the Leibniz rule for the Lie derivative itself by saying that the Lie derivative is going to factorize this way. So first we're going to have the Lie derivative acting on omega, and then we're going to have the Lie derivative acting on v. And that I can make more explicit using the result that we have yet to derive. So I'm just going to write a second line here, Lie derivative acting on omega plus omega alpha. And here we're going to have directional derivative minus the other way. Like that. And now it's just a matter of making the two lines equal, because they are, and isolating this guy, because that's what we want to know. So let's do this. So I'm going to isolate this guy over here. So on the left-hand side, we're going to have the Lie derivative of omega. And then on the right-hand side, so I'm going to push everything else over to the right-hand side. So I'm going to have this, all of this over here, minus omega alpha c beta derivative of v alpha. And then when I throw this over to the other side, I'm going to turn that minus into a plus. So it's going to be omega alpha v beta derivative of c alpha. So that's this line here where I've isolated this term over here through everything else on the right-hand side. And over here, I have all of this stuff there. So here I have c beta like this, plus that. And we're going to see a cancellation. So we see that that term over here kills that term over there. And the rest of it is going to be, what I'm going to do is to factorize a v alpha from the right-hand side. And I'm going to do this by changing the index notation a little bit. So here I have a v that's coming along as a multiplicative factor. So I'm just going to rewrite it as a v alpha by changing the indices over here. So let me write this term over here first, c beta derivative of omega alpha, and then I'm factorizing the v alpha. And here I'm just going to change the name of the indices because they're all repeated. So I'm going to change this into an omega beta. Then I'm going to change this into a v alpha. I have to make sure that I'm summing over the right indices. So I'm going to write it like that with a v alpha factorized. So that's just making those two lines equal to each other. And what I have here is something multiplying v alpha, and on the right-hand side also something multiplying v alpha. I'm using the fact that v alpha is an arbitrary vector, so the result has to hold with respect to any choice of v, and that tells us that what's inside the bracket here must be that thing over here. So that little calculation here where we used Leibniz to define things tells us that the Lie derivative acting on a covector is still going to be the derivative of the object in the direction of the xi vector. But instead of having a minus sign, we now have a plus sign. And what we are left with is now the alpha derivative of xi beta. So it's a different packaging of indices, But it all sort of boils down into something that, gives us a free alpha index on the left-hand side. Alpha down, summation over beta. And we're never upsetting the position of the indices for the covector or the vector field C. So the indices sort of line up in the way that they must. The only thing that is not entirely obvious is that instead of that minus sign, in this case, we get a plus sign. What we don't have here is the antisymmetry property, because the Lie derivative is not acting on the vector, but it's acting on a covector, so that changes that. But what we also have is the fact that this being a proper covector, that Lie derivative being a proper covector, is expressed in terms of things here that are not proper objects in differential geometry, but we can again rewrite this in terms of covariant derivative, because again, and you can verify this explicitly, if you expand out the covariant derivatives here, the gammas will cancel out, as they did before. So again, here, the gammas cancel out. And that's how we can extend the Lie derivative operation to a covector. And then if we wanted to extend this to, higher rank tensors, to, tensors with 2 indices, 3 indices, 4 indices, all we would have to do is to do more of that. And that would give us the rules for Lie differentiation for all of those separate cases. So if you buy the first result for vectors, then after that it's very systematic. You just apply the Leibniz rule. And, I might as well give you a few results that could come in handy at some point. And there's a nice pattern that emerges where, you sort of know how it's going to go. For 3 indices or 4 indices, you don't need to, do that all the time. So the Lie derivative on a 2-index tensor, but with all the indices up, well, the rule is just going to follow pretty much what we had for the vector over here. We first take a derivative with respect to, in the direction of xi. And then we put in a minus sign. And what we're going to do here is to take the first index of the tensor, and we're going to use that as a summation index with a derivative operator. So I'm going to take this alpha over here, I'm going to replace it by a gamma, and I'm going to attach it to a derivative operator. And what's left over is going to be xi, and it's got to be with an index alpha for all the indices to line up as they should. And that takes care of the first index, and then for the second index, we do exactly the same. And now we have that derivative acting on xi with an index beta so that the indices line up as they should. So that's the Lie derivative for all the indices up. If we have all the indices down, well, it's going to be a generalization of what we had there for the covector. So first we have a derivative in the direction of xi, as before. And then we have 2 more terms with plus signs, because the indices are down. And the way it works is, well, pretty much what you would expect from the rule over here. So we're going to take the first index of the tensor, and we're going to sum it over, the index that belongs to xi. So if we follow the rule, we're going to replace the first index of the tensor with the summation index. We're going to leave the second index alone. And then we're going to differentiate with respect to the missing index alpha. And we're differentiating the xi vector. So basically just following the, guessing what we might have from what we have over there for the covector, just applying it to each index of the tensor. So that's the first thing, and then the second term is going to be alpha gamma. So now we're replacing the second index with a summation index, we're differentiating with respect to the second free index, and then we have that. So that's the Lie derivative acting on a two-index tensor where all the indices are down. And then, well, if we want to be complete here, we could have one index up, one index down, and then it would be, well, a little bit of both. So first thing is always derivative in the direction of xi. And then for this alpha index, what we would do is to put a minus sign. We would replace the alpha index with the summation index, and we would combine this with the derivative. And then we would have C alpha. And then for the index beta, which is down, we would have a plus sign. And now we leave the first index alone. We replace the second index with a gamma. And then we have beta C gamma. So you can sort of see how the pattern, generalizes. And, if you can do it with tensors with two indices, you can do it with 3, with 4, with any number. You just, follow the pattern. And the way to prove this would be to keep on using the Leibniz rule systematically. If you're in doubt, you can always go back to that. But, that's the result you're going to get in the end. All right, so the Lie derivative can be defined like this for any tensorial object. We just follow the basic rules like this. And the main message is, again, that this can all be done with or without a connection. We don't need the connection, but we can always replace partial derivatives with covariant derivatives without changing anything. In all of those expressions right there, you can replace all the partials by covariant derivatives, and it's guaranteed that all the gammas will cancel out. And that's something you can try out for yourself just to make sure that this does happen. I guarantee you that it will happen. If you don't find it happening, it means you made a mistake somewhere. Okay. Another thing that's worth noting is that, so the covariant derivative was compatible with the metric, which means that when we do calculations, we can freely raise indices and take covariant derivatives because, covariant derivative acting on the metric or its inverse is always 0. So that's a big help when we do long calculations in GR. We can always, throw in metric factors inside covariant derivatives and simplify everything. Here it doesn't work. So the Lie derivative of the metric is not 0. We're going to talk about that later. So that's why we have minus signs and plus signs at various places. And if we were to convert, this tensor into that tensor by using the metric twice, we would have to work very carefully to make sure that we get consistent results, because the Lie derivative of the metric is not 0, so those operations don't commute. So that's a little warning, because you might come across that. Okay, so the missing part of the discussion is this. So that's what I'm going to turn to next. So proof that that definition over here gives us that. So that turns out to be just a little side calculation that's pretty easy to do, but it takes a little time to go through that. So that's what I'll do next. Any questions before we move on? Okay, so let's do that. Okay, so let's go back to the geometrical picture. So we had the integral curve of xi. We started there. And then we had one integral curve of A, the one that passes through P. And then we had the drag curve up here that went through Q, and that's the curve that was to which the dragged A was tangent. So here's the original A, and here's the dragged A. And then at Q, there's also the vector field originally defined at Q, which in general is going to be different from the dragged A. All right, so that's what we had. And we had a parameter T that runs like this, and we had a parameter S that runs like that. And we had those extra little conditions about, preserving the value of S as we go up in T and preserving the value of T as we go across in S. So all of this was part of the geometrical picture. So what I want to do to set up the calculation is to describe both sets of curves in one go. So we're going to describe all curves as functions of two parameters. So I'm going to make an assignment here where if so I have a two-parameter family of curves, basically, that I can describe through, mathematical assignments like this. So for each value of t and s, I have a specific assignment of coordinates for those curves. And the way to think about this is to say that if s is fixed in those equations and t varies, then that means we're going up along the integral curves of C. So in those equations, if I do this, then we're moving along the integral curves of C. And if I do the opposite, if I let S vary and T is fixed, then what this means is that I'm going across like this, either along the original curve through P or along any one of those drag curves that I get by sliding up by a constant T. So in this case, we get the integral, we get the drag curve. I'll write it like that. And either that one or any one that might live in between, or even the original curve. So, as a special case of a drag curve, we have the original one corresponding to a slide of delta t equals 0. All right, so basically what I did here was to, just choose to describe this mathematically in terms of a two-parameter family of functions that give me the coordinate assignment for those two sets of curves. So if I want to describe the vector field C, I know that I can get that by differentiating those functions over here with respect to the running parameter at constant S. So that's a way of describing my vector field C in terms of a partial derivative with respect to t, understanding that when we take that partial, S is being kept fixed. And then over here, the drag vector field, that's going to be the other partial derivative where we let S vary, but we keep t fixed. So we have two partial derivatives, and depending on what we vary and what we keep fixed, we get our two vector fields, the original vector field C or the one corresponding to the dragged vector field AD. So that's how we set up the calculation, and I'm going to implement this in a very specific way. Just now, keeping in mind that we're going to be working around the neighborhood of P, so maybe we can do this in a way that's really more, a lot more simple than it may seem based on just that. But are we good so far? All right, so basically two sets of curves, and we describe them in one go in terms of that two-parameter family of functions. And either we vary t and keep s fixed, or we do the opposite, and then we get the different curves, and the tangents to those are going to be our vector fields that we defined in the beginning. Okay, so what I'm going to do is I'm going to be working in a neighborhood around P. And we don't have to go very far because we're doing derivatives. So I'm going to introduce a local description of what's going on there in the simplest terms that I can do. So I'm going to say that at P, I'm going to work in a coordinate system such that that's going to be the origin of the coordinate system. And I'm going to say that it's also going to be the origin of the T parameterization and the S parameterization. So I'm putting everything to 0 at P, and because I'm making P the origin of everything. So I can do that. And if we're working around P, that means that everything can be expressed as Taylor expansions around that point. So those functions over here that we started with, I can basically just construct it as a Taylor expansion. The first term is going to be 0 because at P, when T and S are both 0, we're right here, so the x coordinates are going to be 0. So there's going to be no term corresponding to T equals 0, S equals 0, but then we're going to have linear terms, and I'm going to keep the quadratic terms as well because we're going to have to take derivatives, so we're going to make sure that we have enough information at our disposal. So what I'm saying here, and I'm going to make sure to keep the notation straight here, I'm saying that in this Taylor expansion, there's going to be a constant multiplying T. There's going to be a constant multiplying S. There's going to be a constant multiplying T squared. I think that's how I wrote it, yep. There's going to be, so that's, sorry, that should be alpha. There's going to be a constant multiplying S times T. And then there's going to be a final constant multiplying S squared, and then there would be terms that are of higher order, either T cubed or S cubed or anything in between, and I'm going to indicate this as a term of third order. So basically it's just a Taylor expansion of my, functions over here, and I can use that in a neighborhood of P, and I have, just a bunch of constants that characterize that functions, those functions. So just a Taylor expansion. So I'm doing nothing more, nothing less. And all of those things here are constant things that are defined right at P. And they're defined in terms of all the partial derivatives that we can build from that. Okay, so that's the first step. After that, well, if we take derivatives, we get our vector field C and the drag field A. And then I'm going to have to introduce a representation for the vector field A, and then we're going to be in business. So just bear with me. It gets, it gets pretty easy from here on. All right, so we have the function of t and s, and if we take a derivative with respect to t, keep s constant, we get our vector field C. So that's going to be a description of that vector field in the neighborhood of P. So we take a t derivative, we get A alpha. The second term doesn't give us anything. For the third term, we're going to get C alpha T. And then over here, we're going to get D alpha S. And after that, well, we would be down over here. So that would give us, after differentiation, terms of second order. So by doing those derivatives here, we acquire a constant term of first order, and then we would have a whole bunch of second order terms. And I don't want to keep track of those, so I'll write it as terms of second order. So that's what we get after differentiation with respect to t. That's basically following this definition over here. Then if we differentiate with respect to s, keep t fixed, we're going to get the drag vector field A. And so we take an s derivative, so we're going to get B alpha. We're going to get nothing from here. We're going to get D alpha T from that term over here, and then we're going to get E alpha S from the last term, and then we get a whole bunch of terms of second order. So we get our two vector fields, the vector field C and the dragged vector field, the one that corresponds to, the one that's going to be everywhere tangent to the drag curves. And what we're missing here is an expression for the vector field A, the original vector field. And that I'm going to express as a distinct Taylor expansion because the vector field A has nothing to do with those functions. The vector field A is pre-given to us, so it's going to have its own Taylor expansion unrelated to any of that stuff or any of this stuff. So I'm just going to write it as something that would involve a constant, so that would be the value of the vector field at P, plus a first order correction either in T or in S, and then there would be second order terms in the expansion that I'm dropping out here. So basically we get the Taylor expansions here inherited from the functions that give us all the curves, and here we get a separate distinct Taylor expansion for the original vector field A in terms of its own expansion coefficients, and here I'm stopping the expansion at first order. So if we have that, then we pretty much have everything to get going, and it's smooth sailing from here. So I hope the development so far were pretty clear. All right. So one thing that I can incorporate here in the calculation is the fact that if I take my drag curve all the way down to here, I'm getting the original integral curve of A, so that the drag vector field in that limit will be exactly the original vector field A. So when t goes all the way to 0, the drag field should agree with the original vector field. That's in the limit where everything boils down to what's going on at P. So when t is equal to 0, we have that the drag curve becomes identical to the integral curve of A. And as a result, the tangent field to the drag curve becomes the original vector field. So we can incorporate this information and say that when t is equal to 0, well, the drag field, according to the Taylor expansion, that's going to be B alpha plus E alpha S plus second order terms. Whereas the original vector field at t equals 0, well, that's going to be the value at P. T is equal to 0, so it's going to be Q alpha S plus higher order terms. And those two vectors have to agree everywhere on that integral curve. And that means that the value of the vector field at P is actually the same thing as B alpha. And it also means that Q alpha is equal to E alpha. So the fact that the drag vector field has to agree with the original vector field on the initial curve means that while the Taylor expansions are not completely unrelated to one another, we have to incorporate those constraints here in order to make sure that everything lines up correctly on the curve that goes through P. So basically what I'm going to do is to strike this and rewrite the original vector field as B alpha plus P alpha times T plus E alpha times S plus terms of second order. All right. Well, what's the definition of the Lie derivative? The definition of the Lie derivative is that we take the, I have to check again, make sure I have the right order. So it's the vector field at t minus the dragged vector field at t divided by t in the limit where t goes to 0. So here I'm thinking of q as being just a little bit away from p. So it's the original vector field at q minus the dragged vector field at q divided by the parameter distance between p and q, and I'm writing that as t. And I'm just writing this without saying limit. So what do we have from here? Well, take the difference between the two vector fields. So we have the difference between this and that So the B alphas will go away. We'll have P alpha minus D alpha times T, and those two things are the same. So when we take the difference, we're going to get P alpha minus D alpha multiplying T plus terms of second order divided by T. And in the limit, according to the definition of Lie derivative, we're going to get the difference between those two expansion coefficients. Okay, well, great. We haven't learned really all that much, except that we're setting up a calculation that will allow me to show the correspondence between the definition and that that set of operations that we've talked about before. So that's where we're narrowing down on the proof. We're going to show that this is the same outcome as we would get by calculating those derivatives. Okay, so I can only hope that you're still with me. Okay, so before I was looking at objects like this one. I was taking the derivative along xi of the vector A. So that was one piece of the stuff that we had for the Lie derivative, at least in the claim that I wrote down before. So let's look at this. So what I have here is the derivative in the direction of t. So I can write this as the partial derivative of x with respect to t. Sorry, that's with a beta. I can write it like this because xi is, by definition, the direction of increasing t. So I can write it like this, and when I combine those two terms over here, what I'm really talking about here is the partial t derivative of my vector field, keeping s constant. Because if I'm saying partial with respect to t, that means that I'm keeping something fixed. And in the context, it's clear, I think, that what I'm keeping fixed is the second parameter s. So that's something we can calculate because we have our vector field A expressed in the form where we can actually differentiate. And the other thing that I should have said is that all of this will be evaluated at p. So we're going to evaluate this at s equals 0. And if we do that, then if we take the derivative of A with respect to t, we get p. And that's the result for that derivative. And that happens to match what we had up here. So that p alpha is something that I can recognize after the fact as being the t derivative of A or the derivative of A in the direction of the xi vector. So we have that, and that's what we needed on the right-hand side right here. And now the only thing that we have to do is to say, well, the other remaining ingredient was A beta derivative of xi. And that is a little bit more tricky because I'm talking about a derivative in the direction of A, not a derivative in the direction of the drag curve, so it's not quite an S derivative. So what I'm going to do here is to write this as the derivative in the direction of the drag vector field, AD instead of A. And I'm going to make up for this by taking out the difference. So that's just an identity, and the reason why I'm writing this is because this is something I can identify as the S derivative of the xi vector. So that's something that can be expressed along the lines that we had up here. And the difference over here, well, the difference between the two vector fields starts at order 1. And when we take the limit, it's going to go away. So that, in fact, doesn't contribute to the result. This over here, well, that's going to be the S derivative of my vector field, C. And that's going to be evaluated at P, therefore at T equals 0. And when we calculate that derivative, we go back to the expression up here. The S derivative of that, evaluated at T equals 0, is going to be d alpha. So when all said is done, when it's all said and done, we have d alpha coming out. In the limit, this goes away. And we get only that. And the d alpha that we get over here was precisely what we had up here. So the conclusion from all of this, after all of this little setup and this side calculation, is that sure enough, the Lie derivative of A is the derivative of A in the direction of C minus the derivative of C in the direction of A. The derivative of C in the direction of A. So we take the difference. That's the same minus sign we had up here. And I think the calculation establishes that what we had defined here in geometrical terms amounts to operations that we can do, in terms of coordinates or in terms of basic manipulations that we, that will involve, taking derivatives and doing things like that. So I hope you were able to follow this. I think I'm seeing some puzzled faces. If you had, if you had a struggle here, I've posted a document where I go through all of this and explain in words what's going on. So maybe you'll, benefit from a second pass through this. I think the calculation by itself is not that important, but what's important here is the concept of the Lie derivative and the fact that we can write it in terms of more sort of elementary operations and do all of this without having to introduce a connection. If we don't have it, we don't need it. If we do have it, we might as well use it. So we can replace those partial derivatives by covariant derivatives if we want to, but we don't have to. And the whole point is that the operation is independent of a connection. For that matter, it's independent of a metric. The metric never occurred anywhere here. So it's a completely primitive thing that exists, each time you have at least two vector fields to play with, or a vector field and a covector field, as we saw before. So, we're going to see how this applies. We're going to see what good this is for, because I'm not just doing this for the, for the fact that it's also pretty and so on. It turns out that there's applications of this that are crucially important, and that's the kind of thing that we'll start talking about now, except that we're out of time, so I'll have to wait until next time. All right, so I did see some puzzled faces, so I'm not convinced that you've all followed this calculation, but anyway, I think you'll have a second chance if you go through that document and try again. You'll have to take my word that, okay, if you didn't follow all of this, that's fine, but hopefully you'll know what this means in terms of, geometry, and that connection over here, well, that's something maybe you can take for granted and verify for yourself that this is something that gives you a proper vector in the end, even though each individual term in this equation is not a proper vector. They're still combined together in a way that defines something that's properly defined in terms of geometry. So that's really the essential point here. So what we'll do next time is to see where this applies, and basically we'll see that the Lie derivative is the correct way of expressing this notion that we might have symmetries present in space-time. We'll express this as the statement that the Lie derivative of the metric in a certain direction will be 0. So that means that the metric is, when dragged in the direction of that direction, invariant in a very specific sense. So we'll talk about that, a very important, connection with symmetry properties. So we'll talk about this, and we'll talk about conserved quantities that come with those symmetries, as in Noether's theorem. So, there's a lot of good stuff that follows from this, and important for people to know. So, any questions before we stop for the day?
Are there any other derivatives?
Yeah, so there are other derivatives that can be defined even without the connection, even without a metric. So the exterior derivative of forms can be defined also, independently, but those act on very specific objects, so they don't act on arbitrary things. So there's a caveat there, and there's probably all sorts of other derivatives that have been invented, but they tend to be combinations of these things.
Right.
So I think those are the three main ones anyway: Lie, covariant, and exterior. Yep, Hassan.
Yeah, about earlier, what was wrong with considering the drag to be coordinate transformation again?
Oh, there's nothing really wrong with it. So I could introduce the dragging as a coordinate transformation from one point to another point. It's just that I don't find that particularly attractive, and I find that it sort of detracts from the geometry. And the geometry is all about, taking a curve and shifting it in a way that doesn't require a coordinate system to describe, at least in terms of, geometrical terms.
And we want to define that algebraic form. We are using coordinates.
Yeah, so to relate this, which is completely geometrical, to something like this, which is more, given in terms of, elementary operations, there we have no choice. We have to introduce coordinates. But the coordinates here are just used as, as a guide. In the end, we end up with something that, could be defined in any coordinate system. So there's it's basically a point of, conceptual. So I'd rather, so I like this point of view because it's more geometrical, and you see the underlying, reasoning behind it, as opposed to, let's write down the coordinate transformation and let's do some, sort of blind things, as opposed to things where you see what's going on. Okay, yep.
Do people try to replace covariant derivatives by having somehow only Lie derivatives?
Could you do all the physics without covariant derivatives?
You have to single out some special vector field.
Yes, so you would have to do that first. You would have to at least know that you have at least one vector field, like C, that would be there for you to use at all times. So that would be a restriction. So presumably that means that some of the physics, you would be restricted because of the assumed existence of that vector field. And I think, but more than that, I think it would be a matter that, for some things, the covariant derivative operation is really the thing you want, like to describe geodesics and to describe, things like that. Whereas for other things, mostly tied with symmetry operations, the Lie derivative is really the thing you want. So they really do different things well. So you could do a lot of, you could do everything without the Lie derivative, but it would sort of cloud some of the issues, and the other way around is true as well, I think. Yeah. So yeah, we need both. Yeah. Okay, very good. Thank you. So we'll pick this up again next week.